Entitled relative entropy method applies to the stability of shocks for system of conservation laws.
Thank you. Well, actually, now I'm in Oxford, but I'm not sure that I have to say it here, okay? So it's better to say that I come from US, right? Yeah, so first I would like to thank the organizer for the invitation. It's a great pleasure to be here. And I will talk about relative entropy. Yeah, I guess it's better not to use this one, right? Yeah, begin this. So relative entropy and shock stability. Stability for shock for conservation laws. I will show that actually the motivation actually is linked to kinetic theory, even if it is more actually conservation laws in terms of result. And this is a joint work with Nicolas Léger, which is a former student of mine, which is now in Carnegie Mellon. So let me first give you the framework, which is actually very standard in conservation laws, but let me do it slowly here. So basically what I'm considering here is a system. So the unknown will be function of Tx. Okay, so let me write it down. I have this with me all the time. So a function of time x. Okay, so this means this is a monodimensional problem with values in, well, it's a system. So let's say it's in Rm, and actually it will be bounded domain over Rm. Okay, and I'm considering an equation of the form dtu plus dx of a of u equals 0. Okay, so a of course is a given function, so this is, let's say, which is C1, for instance, of nu. Okay, so well, you can write in this form, for instance, well, I'm mostly interested in fluid mechanics, so for instance, a compressible Euler equation, okay, full with temperature or not. And in this situation, I will consider only such systems which have a convex entropy. This means there is a eta, which goes from nu, which is in Rm to R, and I want it strictly convex. Okay, and what it means to have a strictly convex entropy, it means actually you can construct, well, this is, well, an associated entropy inequality, which is d theta of u plus dxg of u, which is non-positive. Okay, so this is very classical. Of course, all system does not have this structure, okay, because actually, well, again, it's very well known. The fact that you have this structure means that actually you have some condition on G. This means that actually G prime of u, which is actually a vector, because G, well, I mean, lies in Rm, the u lies in Rm, can be written in the form eta prime of u, eta prime of u. Okay, and the fact that eta prime a prime can be written as a gradient is a strong structure, especially it implies that a prime of u is diagonalizable. Okay, and okay, so from that, actually, I will introduce the relative entropy, which again is very standard things. And basically, I will call relative entropy. So this is a relative entropy of some state with respect to another one, with uv in u. And by construction, these things is eta of u minus eta prime of u, u minus v, minus eta prime of v. Wow, what I write, yeah. So this means basically this is eta of u, and you take out the linear part, linearized part with on v, okay? And the good thing is that actually if you are strictly there is no prime. Yeah, sorry. So, yeah, I was confused. So let me write it down the correct way. Well, the usual way, minus eta prime of v u minus v. Okay, it's better. Okay, and especially, so it's very well known again, if you have, if you take, for instance, a domain omega, which is compactly in U can be an open, okay? And then actually when you consider eta of U and take U in U, V in omega, and actually eta of U with respect to V, this thing, there is two constants depending on omega, such that this is comparable to the squared of U minus V. Okay, so this is basically why this quantity is interesting. Well, in the context I will use it, it's interesting because actually it's a kind of distance squared. Okay, so you can use it as a natural distance. It's a kind of natural distance associated to the system. Okay, well, so when you talk about these kind of things for conservation laws, so actually it's been used, and the idea is to actually to go further those results of Dafermos, and Dipernat, and especially paper of Dipernat of 79. And what this thing was used to show actually the L2 stability. So L2 stability of Lipschitz solution to 1 to this system. Actually, when it is Lipschitz, it verifies this also with inequality. Okay. And basically what they've shown is that if you take V, which is Lipschitz solution, which is Lipschitz, okay, and U, weak solution to 1, 2, well, then actually you can consider this kind of distance, so the relative entropy of U of Tx with respect to V of Tx, dx, and this quantity actually can be controlled as a big exponential with big Ct of the same thing at t equals 0. So eta of U0 with respect to V0 dx. Okay, so it's a very strong stability actually, because it means basically that if you have something which at t equals 0 is, let's say, order epsilon, then these things, after a big time, stay over the epsilon. Okay, multiply by a constant, but it's stay over the epsilon. Okay, so this means it's really epsilon, stay epsilon. So very strong stability. I have to say, I will say later, but actually they did also things. I mean, Dipernat works in this very nice paper. Actually, was also doing things for system, but it was only uniqueness, not stability. Okay, at this time. But I will talk about that later. Perhaps I should keep this for you. Yeah. Okay, and there is also other use of the relative entropy, and of course, while in kinetic theory, so for Boltzmann theory, this is also a notion which is extensively used. We've seen it like in the talk of Aoki, and there was some thing cited. I will also would like just to mention result who use this kind of things for asymptotic limit. So asymptotic limit. Most of the time, the first result that we cite for relative entropy used for asymptotic limits is the result of Yao in 91. It was in another situation. It was for Gainsbourg-Landau equation, but it was to show actually the convergence on some models. There is another one that I like very much. There is a lot, of course, of work on this kind. So there was also almost at the same time a work which was, I mean, a program which was proposed by Goltz-Livermore, Bardos-Goltz-Livermore. To go from Boltzmann, so it's hydrodynamic limit, Boltzmann to incompressible Euler program, which has been completed later with especially with Lorsin-Raymond on top of those people. But basically, well, why is but it's incompressible, okay? So at this point, it does not include these kind of things. And what is the main idea is that actually when you have a very strong, all those limit problems, it is Gainsbourg-Landau here, incompressible Euler here, are very stable. I mean, the solution are very stable in this sense. So basically, the idea is when you have some limit system, limit solution which are very stable, then basically you just need consistence. If you have consistence, then all the nonlinearity are driven just by the stability of the things. So the question is, what can we do for now when you are compressible, okay, when you have the compressible situation? Well, the good thing is that actually we can show that this good structure, these things, is enough actually to do a dynamic limit. So these things actually which is, well, I've done several works on that with several collaborators, so especially there was with Berthelin, Savaras, Amélie. But basically, it means that you can have this kind of dynamical limit as long as the limit solution is Lipschitz, well, smooth enough. Okay. The question is, what can we do in terms of shocks? So this was basically my main point. And let me show you right away that you don't have this result is actually wrong for system. Okay, and this is very easy. Well, let's take Burgers. If you take Burgers equation, so it's just dtu plus dsu squared equals 0, take a very simple shock. This is a good example to understand what goes wrong. So you take 1 minus 1. This is a steady shock, actually, for the system. And if you take perturbation, so let's say, so this is my V for you. Okay, I want to show that this V actually is not stable as like this. And if you take a perturbation, well, it means that here you take something which is order epsilon. Okay. And well, if you look at, well, since this relative entropy is related to the squared, okay, actually you can show that the L2 norm for this is order epsilon. Okay, so this means that here the perturbation U minus V and L2, which is almost square root of the entropy, so it's of order epsilon. But now if you make this, you see how it goes in time. When it goes in time, this means that the velocity here, you have a shock, but this is not the good velocity, so it means that you will have something like this, okay? And actually here, this distance is over the epsilon. Okay, so this is order the change of velocity is over the epsilon. And so you see that the difference with actually this state is these things, which is in L1 norm is over the epsilon, but now in L2 norm you can see it's over the square root of epsilon. Okay, so now the U of t minus V of t L2 is over the square root of epsilon. So this means that, I mean, it's small but not that small compared to epsilon. Okay, so you keep this very strong structure small and with the same amount of smallness. Okay. This is something, of course, which was again very well known. This is basically what well, one reason that the L1 norm is so much used in conservation laws, okay, because L1 is fine, L2 is bad. Well, basically, what I want to say is not actually it's not that bad. And I would like to introduce the theorem. The theorem is the following. So now, before the theorem, I should say what I'm consider. Let's put it here. What I consider now will be for a system. Okay, so I consider now a system, and I will take a given shock. So you have a left state I call UL, UR state, and a certain velocity sigma, and I assume that this is a steady. I mean, not a steady because it can be sigma, but this is a shock. Okay, this is a shock solution of my system. And my claim is that so if you take UL, UR, sigma, one shock, I will explain this, why I call it a one shock, and how you can extend it slightly, okay? So take a one shock, and take U weak solution to my system, verifying on top of it what I will call very strong trace property. I will explain this also. It means it's not only weak. Slightly, there is something, slight things on top of it. Then what I need, I guess, is it. Then if at t equals 0, you have both the integral between minus infinity to 0 of eta of u0, v0, dx, which is smaller than, let's say, epsilon 4, and the integral between 0 and plus infinity of eta of u0, v0 are the initial values, okay, dx, which are order epsilon. Then you keep this structure for time. Then you have, there's a lot of them. Well, up to something. So this means actually the integral between minus infinity to a function x of t of eta of u of t with respect to v of t dx stay actually exactly of order smaller epsilon 4, and for the other part x of t plus infinity of eta of u of t. So actually, sorry, yeah, no. It's UL. Let me write it down, and then I will explain things. And you are dx is smaller than c1 plus t epsilon. And what else I should have said? There exists x of t, which is Lipschitzian, Lipschitz of R plus. And on top of it, I put everything here, x of t minus sigma t, which these things can be also controlled by a constant square root of epsilon t. So let me do a pitch. Yeah, I need to keep this, right? And here I'm not allowed. Okay, so here. It means that actually I've shown on the here, I've shown the worst scenario. This means that actually what happened is that if you have some, well, let's forget about the epsilon 4 right now. What I claim is that up to a shift x of t, up to a shift, the shock is very stable. It means that if you have a certain structure, you keep it in epsilon, you keep it for all time. Okay? So it means that actually, well, what is unstable is actually the position where if you have something which looks like your shock, okay, it will stay that, well, the profile will stay that like this, except this position here may be shifted, okay, because you don't have the right shock. And this is the x of t. And this x of t actually is of the square root of epsilon. Okay, but if you forget it, the rest stay very well separated. Okay, so this is the basic idea. So basically, it means what? It means that you have still a very nice L2 structure, but up to a shift. Okay, and the shift depends on the solution itself, on the solution U. Well, I should at this point state the hypothesis, because of course there is some hypothesis for this to work. The first one, yeah, so I said the very strong trace, so let's put this aside right away. What it means for you to have a very strong trace, basically, well, this is technical. It means basically that for any, let's call it y of t, so such function Lipschitz of this kind, actually fixed, so you fix this. Then for almost every t, you can define a limit on the left and on the right. Okay, so this means you can define ut of y of t minus and u of t y of t plus. Okay, so let me do perhaps in tx. So this is in x, this is in t. You have for any y of t Lipschitz that you put here. Then now, for almost every time t, you can define the limit on the left and on the right. Okay, so basically, if you have a BV log function, it's fine. Okay, I call it very strong trace because it was related to the notion of strong trace that I've introduced a long time ago. Unfortunately, you need slightly more. Okay, the trace in terms of L1 is slightly. I mean, slightly. So this is something which is. I'd like to simplify this, but let's put this. This is technical. Okay. So this is on here. So you see, you don't need that much. You need a weak solution which have on top of it this kind of structure. But now, of course, I have to state some hypotheses on the system. But you will see that actually they are very natural and quite. So let me present it. So this hypothesis on the system. Well, let me state them for the expert, and then I will explain on the picture what they mean. But I would like to say right away they are very classical in this kind of situation. Okay. So basically, what you see that actually I claim this is a one shock. This means that I refer to a family, to a one shock family, and I will assume something on this one shock family. So I assume that this one shock family is what? Is U. So verify the criteria of U, which is called like this. I will say what it is, okay? But this is, it has a name, so it's very classical. And on top of it, that along the family, the strength of the shock increase, which is also very natural. The strength of shock increase along the family. And you will see, actually, I will write it exactly, this is the strength computed in terms of the distance that we have, the entropy, the relative entropy. Okay, this is the thing which comes up. What I need on top of it, I need that the other family of shock. Classically, if you have Rm, you will have M family, right? So the other family, all of them are lax. Basically, it means just that they decrease their entropy. That's it. I really need very few on that. It's very natural. And the last thing is that says that the one shock family is well separated, what I call well separated from the other. Which shockingly is, of course, like this. This is also, so I will say what it means. This is also something which is not, so for this one, there is a lot of systems which does not verify this, but there is a lot of theory which use this, okay? And basically, what I mean by this is just to say that for any, if you have a shock, you have a speed, and for any speed which is of this, which is not a one shock, this speed has to be bigger than the first. I will explain why it's natural, okay? The smallest eigenvalue, associated to a prime of U, okay? So it's also something which is used a lot. Okay, so let me do a picture to explain this quickly, and then say that actually it's give you some typical example when it works, okay? And okay. Yeah, so there is a typical theory when you get conservation laws, when you have, so this is nu, this is the state of possible state. Let's say, for instance, R2 is correspond to a system 2 by 2, okay, so it's like here. And for any state that we could call UL, U left, or U minus, because it can be different from this one actually. Okay, U minus. Well, classically, you can look at all the shocks with joint UL, so this means that such that UL something that I will call a family. So there is two family basically of state like this, such that UL S UL of sigma. So you have some family with a certain, so let's say S with sigma. This is a shock. Okay, so it's a family that are indexed by S, such that U minus on these things gives a shock with a certain velocity. Okay, and finally, well, classically you have, so in this situation, two family like that. So I can index them, okay, and they can be parameterized by the eigenvalue of a prime of U. Okay, I said that actually when I have an convex entropy, I know that this is diagonalizable everywhere. Okay, and you can parameterize them, and the one shock corresponds to the smaller one. Sorry? Sigma depend on S, yeah, thank you. Of course, yeah, exactly. So this means that my one shock here corresponds to the smallest eigenvalue, okay? And I correspond to this case. So you see that actually when, everything, the result is sided, okay? And it uses the fact that actually we have a one shock. This is why it is sided. And, and what I wanted to say, yeah, and now, okay, so if you want to, what means U, it means that along this line of shock, the derivative with respect to S, so of course it depends on S, this thing is negative. So this means that actually when you increase the shock, the velocity is decreasing, okay? So it's something, well, not always true, but very also for gas dynamics it's always true, okay? For the system I consider. So this is what it means, U. And what it means, the strength of shock increase, it means that along this shock, so this is the one shock, okay, my main one here, actually is entropy. When I compare the distance of UL, U minus, this one, with respect to this, to the SUL, so it's for the first one, okay, of S. This thing is a function of S, okay, because you consider, and you just want that this to increase, okay, which is also very natural. Okay, so this increase in S. Okay, so in some sense, it means that along my family, the shock is stronger and stronger, but measured with this metric. Okay, and this is what will come up naturally to get that. I think I have. Okay, so this is what it is. This is the only assumption. Actually, we need even less than that. It has only to be local and so on, but I don't want to go there. Well, we can use this. Well, the typical example is fluid mechanics. Fluid mechanics. And you can take Euler. And for Euler, so the 2 by 2, so this is gamma laws, what we call gamma laws. Well, it works fine, so it's 2 by 2. And for 3 by 3, works for shocks. So here I'm cheating a little bit. This is actually the result, works also for contact discontinuity, as long as they add one extremal. One, here I put everything on one, you can reverse and add for the other extremal. So it does not work for middle one, okay? So this means that here, all the in 3 by 3, all the real shocks, which are not contact discontinuity, are extremal. So it works for all of them, okay? And it works even if you consider a vacuum. So it means there is no problem to consider vacuum on the U. On the final one, the V, the shocks are no vacuum, you cannot contact vacuum. But the U can have vacuum, and it's completely okay. So this works completely fine with this kind of theory, so with vacuum. Okay, so you can see it. I should talk about the previous result at this point, I guess. I have to go back to the seminal work of Dipperna. Actually, it is written by Dipperna, but for some reason we put always Dafermos also with it. So let me write it that way. This is a result of 79. And I already talked about it before. It was for stability of solution when the limit is regular. But actually, even in this work, it gives some hint how to work with system. And what he showed is actually the uniqueness of the solution. So there is no L2 stability, but there is already the notion of showing by this way the uniqueness of the solution. Okay, so you can see actually this result as pushing forward on pushing more we can on the result of Dipperna-Dafermos. I should cite also. Work of Chen Fried. So there is a list of work of them. So it's 01, 02, 04, and one of them is with a third collaborator, Lili. And basically, what they've shown, so they already pushed a little this, so they were also uniqueness. They were also able, and well, basically there was some assumption here that it was relaxed, no smallness in L infinity, but also L2 stability in large time. So asymptotic L2 stability, asymptotic in time, L2 stability. And what I should say, and well, well, also, so it works basically. I think that all the proof was in context of Euler equation, but even in 3D, and in this case, actually, they were able even to work on the whole 3 by 3, even with the contact discontinuity for this case. But at this point, no L2 stability in the sense that I write here. And of course, I should also cite the works of Léger, who did basically this for the scalar case. So in some way we can see it also as an extension of this work too of Nick. Okay. So this is a project actually I have for quite a long time. But this is where we stand. Okay, so this is here. So as you know, I will give you an idea of the proof. Okay, how things work. So the proof. Well, and let's talk about difficulties in the proof. Well, before talking about difficulties, I should say, well, here you can see that actually at the end, what we are interested in is what? Is to find, we want to find this x of t, so the difficulty is basically to construct x of t, construct, okay, x of t, and of course we have to construct it on the fly, because, well, the examples that I've given on burgers show that actually depends of the value that you have, you know, the exact value, because you can push your things just because the value is moving there. Okay, so it's really on the fly that you have to construct it. And at the end, what you want is just to compare u with respect to the left state ul on the left of x of t, and to compare u with respect to u plus on the right. So at the end, you want just to compare with constant. Okay, and when you want to compare to constant, actually, well, for any, let's say, c constant, you can write an equation for this quantity for the relative entropy. Well, very easily, and actually you can show that you have d over dt of eta of u. So u is a solution, c is a constant, plus dx of something that I will write f of u c. So for those who read the paper of Diperna, I'm sorry, it's perhaps a little bit confusing because I've changed all the variable. Basically, it's not by game, it's just because actually we did it and then we read the paper of Diperna on things that there was actually a lot of things that we could have saved a lot of time by reading it at the first place. But so I keep my notations, okay? And so you have something like this. So and where's my function u of c is not very important, but let me write it down. Is actually g of u minus g of c minus eta prime of c eta of u a of u minus a of c. Okay, so you can, I mean, you can just compute it. This is a function like this, and it's not that, it's very natural that you can get like this, because actually if you remember, what is this? This is the entropy eta of u plus something which is linear in u, okay? So any function which is linear in u is an entropy, so it's fine, and you just add two entropy, okay? So you add the two corresponding things, you have a, so it just says that this is an entropy also, okay, when you compare it to a constant, okay? So it's fine. Well, and so basically what you want to do, well, the idea then is to say, it's a bet in some sense. And the bet is to say that if you have a situation of one shock, the one shock is really pushing hard to the right, okay? It's really pushing hard to the right. And so this means that if you make things work on the left, things should go fine on the right. So this means that actually I want to construct my x of t, just to make this on the left decrease. And actually you see I didn't put some c, it's exact, same epsilon 4. So I just decrease on the left. I define my x of t like this. So how I want to do it? Well, here you just want to integrate in x, and basically what you want to say is that d over dt of the integral between minus infinity of x of t of this quantity. Okay? If you consider this quantity, what it is, well, I just use this equation. This is smaller or equal. Let me put it here, perhaps, or here. It's smaller than what? It's smaller than f. It's f, yeah, of u. So here I have a strong trace. So I can define actually u of t, the trace as x of t. So perhaps I should do a picture to say what I mean here. Okay. At a given point t, I have my x of t, which is here. Okay, and I will just look at the left. I have my ul. I have something here. I want to compute the difference of that. Well, so here it depends on the value on the left of my solution, which can be discontinuous, right? So this is u t x of t at the point x of t minus. At one point, I will call this u minus, okay? F with respect to, well, I compare it to ul. So this, so these are the things. But on top of it, you have, of course, a translation, x of t. So this is minus the derivative x of t of eta of u of t x of t minus ul, okay? And at this point, I can write the other one that I will use. It's on the right, and here is quite easy. It's the same thing. So it's d over dt of the integral between x of t. So now on the right, compare it to ur plus infinity of eta of u of t with respect to, so it was ul, now it's ur dx, and these things is smaller, so now it's a minus sign, okay? So it's minus f, and let me write it u plus at time t, okay, which is, but the limit on the right is this value. ur plus x dot of t eta of u plus of t ur. Okay, so you have those formulas. So it's very simple. Now my claim is that actually, well, let's try to make this, let's try to compute x of t to make this equal to 0. And actually even slightly more, okay, because I want slightly more. So let's say that I want this to be smaller than, well, let's say very small. Well, first negative, okay? And if you want to find negative, well, you see it's just you compute x dot, okay? It gives you x dot. And this means that the x dot that you want to have is just given by x dot equal f of f, okay, so let me write it little f of u of t x, okay, so you have, yeah, so let me write it at this point like this, x of t minus this, okay, and with respect to ul, right, okay, where I define it just f of u minus ul divided by eta of u minus ul, okay, it's very, very easy. I just want to get 0. And for some technical reason, actually, I will take minus epsilon, okay, I can say, let's do, okay, I have a certain velocity, let's actually go slightly less rapidly, okay, which means that doing this, I go not that fast to the right, a little bit to the left, and if I go to the left, I eat up more bad entropy on the left, okay, slightly more. Well, okay, so this is the idea. Well, the problem is, of course, to construct this is not that nice. First, f of, let's call it as a function of v ul divided by eta of v ul, not well, actually, it's discontinuous for v close to ul. So there is first, I mean, if you have a function, and I mean, you want basically to have a Cauchy-Lipschitz function, and it's not even continuous, okay? Because actually, when you take v close to UL, this can go to all the, well, something all between all the eigenvalues of UL prime. Okay, so it's something that does not work. Well, and so this can be solved, but of course there is another problem, which is obvious, is that actually u of tx, u of t as a function of tx is not Lipschitz. Okay, the weak solution, you can have some jumps. Actually, I write it here. And actually, sometimes you can want to stay in the jump. Okay, these are usual things. This means that Cauchy-Lipschitz cannot work. So actually, what we do, and what Diperna done actually at this point, is using a sort of well, actually we have to construct them. But this idea is to get some kind of Filippov flow. Okay, so you get some Filippov flow, and you hope that the way you construct it, you still will verify these kind of things, and you still want to have the function of u to be continuous. So actually, it's not the good one. So the one that you take equal, let's call it v. That this is look like a sort of Cauchy-Lipschitz things. V of u of t of x of t, actually minus ul, and this v will be, so the f of what we want here, which is f of u minus ul over eta of u minus ul, and the first eigenvalue minus epsilon. Well, we've seen that actually this comes naturally when we look at the paper of Diperna. This was the one he was using, actually. It was this one. In some ways, the worst case, which kill everything. Okay, so in some way, here now we take the inf. Doing this actually makes this continuous at this point. Okay, so at least we have a continuous function, and we can define Filippov flow, which means what? It means that the Filippov flow is that actually we have something which is almost like this. Actually, it's an inclusion, and then we have to check that we have what we want. Okay, but we have basically what we want on the left. So this means that doing this, we can show that actually on the left, these things for almost every time t is negative, but even slightly more because we multiply by epsilon. So it's smaller than minus epsilon eta of u minus ul. Okay, so what is this quantity? Is exactly the distance there. Okay, squared with this quantity. Okay. So this means that what? This means that first, well, I remind you, the relative entropy is a kind of distance squared, so it's non-negative. So at least we get the first part. Okay, this thing is decreasing. So if it's epsilon 4, we stay at epsilon 4. Great. Okay, and this was the point. The point is to say, let's try to deal with the left part. If we deal with the left part, then we hope that everything will be fine on the right. Okay, so now we have to check that actually on the right it's okay, because we try to be not too brutal, but still. And well, so the first thing is to say, well, on the right, what happened? Well, first, let's see still on the left, and let's see what happens. Well, you see, we want at the end to show that this function converges to ul, and everything depends pointwise here. Okay, but let's say that this point, let's see what happens when this point wants to make a fool of itself and to be far from ul. Okay. So let's take I, so this is a time, such that u minus want to play crazy, and b, let's say u minus with respect to ul is pointwise. Okay, so value here, and the distance here is, let's say, bigger than epsilon squared. This means the distance over the epsilon. Okay, so this. Okay, and you will see this is where the epsilon 4 come into play. But because here, well, there is not much that we can say, because if you are far on whatever, then you really don't know what happened on the right. But what I can say is that actually I control those bad guys, because this cannot happen very much, because on the left you have just epsilon 4. So each time you have on such a time t, here you lose epsilon 3. Okay, and you have epsilon 4. So actually it can happen only on the volume of time, which is over the epsilon. Okay, because this is epsilon 4. Each time it makes crazy, it's epsilon 3. Okay, so you can do it only for the time epsilon. Okay, so this means that when you have this, it can happen only there, and then now when you look, what happens there? Well, when this making full of itself, well, you cannot say much, but you can say it happens not very much of time. So here, perhaps you have something bad, but at the end, the volume of this is of epsilon. Okay, so it will be over the C epsilon. So it's fine. You have epsilon at the beginning, it's still over the epsilon. Okay, this is why we have this equivalency. Okay, and otherwise, wow. Otherwise, here we control the guy. Here. So now we can consider only the case when this is control is close to UL. And now we have to see, well, what can happen when you are close to UL on the right? And especially about, so here you have, now you have your U minus and you have your U plus. So well, basically there are three cases that you have to consider. The first one is when it is continuous, actually it can be. Okay. Well, by the way, if it is continuous there, it means that we can go further here, okay? Because actually here it's close to UL. Okay, so this means the velocity is fine. And here, well, basically, if you are close to UL, it's just a computation, right? It's just a computation because what you have get is this. You replace UR, well, you replace U plus by something which is close to UL. Okay, so basically, you just have to compute this value as a point, which is minus F of, so U of plus, well, it's close to UL. So let's write what it is when it is UL. So it's a sort of perturbation, epsilon perturbation, so the rest will be order epsilon is fine, plus x dot of t, and the other one is eta of UL UR. So you see it depends only on your actual shock, UL UR, and this velocity. And here, well, you want to do what you want, but actually what you, here, you can say that actually we consider the worst scenario, okay, this is the nth. And you can check that this is, so it was the nth. So the worst case is when you take lambda minus of U, L. Okay. And now you have a formula when you replace this. So it's the worst scenario is when here you have this. And now it's a formula, okay? And you can check that for systems this has a good sign with the assumption that I have. So it's just checking on UL that this is fine. And then this is the epsilon modification of that. So it's good, okay? So it's fine. So now, well, the other scenario that are interesting is the shocks. When actually here you stay, and of course it's almost every time. So it's when you stay actually in a shock, which actually, I guess if you do some numerics, would happen a lot. Okay, so most of the time actually you stay in shocks because, I mean, if you have some shocks, this is where you want to be in order to minimize the entropy. Okay, and there's two kinds of shocks. This shock can be a one shock or another kind of shock. So this is why there is a two case. And let me show you that first, that it is a one shock. Because if, so it means that U minus, okay, for my actual solution here, U minus U plus, with the velocity x dot of t, so then you fix t, okay? And actually you can show that for almost every time t, this has to be a shock of the actual system. Okay, so you know that you can just consider this scenario, and if it in my claim is cannot be a high shock, and why? Because I know that x dot of t by construction again, and this is why this quantity actually is important, because if these things is the nth, so nth of both, so this means what? If I take nth, this means that I'm always bigger. Right, so it's always bigger than lambda minus of U minus. Okay, but the well-separated assumption says that actually for a high shock, this cannot be. Okay, so this, no high shock. High shock for I different from 1. Okay, so it means that actually we just have to consider the one shock. This is the only case which matters. And for this case, so let me be clear. Now what I want is to control this quantity when U plus is a one shock associated of something which is close to UL. So again, up to epsilon perturbation, the situation that I want to consider is you have your state here, you have UL, and U minus is almost UL, let's say it's equal, okay? Basically, I just want to consider when I am here. And I have a shock here, which is along the 1. So this means that if I do my things here, UL, UR is on my curve one shock. And now I consider here another point, which is U plus, such that UL, U plus is a shock, and UL, UR is a shock. They are all on the curve of one shock, okay? And here there is a very beautiful, let me call it lemma formula. So actually, well, I was very impressed because it's Nicolas who found it. And when he got it, I said, wow, that's so nice. And actually, when we read the paper of Di Perna, it's almost there. I mean, it's basically there. So it was a big disappointment, okay? But okay. So at least we have, I think, a better way to write it with respect to the strength of eta, the strength of the shock. And what says this lemma? Will I be able to give it? It's a very nice formula, so I'd like to, even if you don't remember it, just to show you. It's very nice. So it is basically the quantity that we want. So you take f of, and let's say that u plus is, so it's along the curve, okay? So it's a certain s, sul, okay? Along the first, for a certain s, it's parameterized by a certain s, okay? And this one for a certain s0, L1, S0, okay? And the S0 is bigger than S, okay? This is the things. And we have, for any S, we have the formula that so this is U plus. So this means if I consider U plus with respect to UR, they are not related by shocks, okay? They are related by shocks through UL. But since you can compare this, this is UL of S with respect, I said S, yeah, so let's stick to the notation of S0. So these things with the minus, because this is a good things, okay? So this is plus. And sigma of which one? Of S. So the sigma associated to this shock, okay? The quantity eta of same things, okay? SUL of S with respect to SUL of S0. So the exact thing that we want, this thing is equal to minus integral between S and S0 of what? Of sigma dot related with S of tau. And here this is eta. So here is with respect to UL. So it's UL with respect to, let me put a plus on the, U plus minus eta of UL with respect to UR, okay? D tau. No, I cannot write it that way because here it has to be S of tau. UL1. Yeah, I think this is it. And okay, so this is the formula. You see, you can write the exact quantities that we want for any S along all this curve. Okay, you fix those 2 points. You take any things here. Well, this is the formula. You have this. Okay. So I said S0 is bigger than S, so the integral is fine. Here you have a U shock, which means that actually the velocity is decreasing. Is decreased when you increase the shock. Okay. So this is not positive, and this you want this non-positive. And I hope that I didn't mess up with the sign. And basically, it means that for all shock here, the strength of this shock is smaller than the strength here. Okay. And then you have a sign here. This is also negative, negative, positive, negative. Okay, that's it. So this means that when you are an actual shock along these things, it works. This was used actually when you write it carefully by Di Perna, except that he didn't write this, I don't know why, he didn't write this quantity like this. He write it with respect to the gradient of eta, well, in a formula which is integrated. I think it's nicer to write it that way. Well, so basically you have here, you have all the situation, you've seen all the situation when you have a shock, when you have no shock, and you just check that actually up to epsilon, up to a perturbation, it is fine. So you play with the perturbation and you see what you get. Well, to get this is just by integration. Okay, it's just a conservation of stuff, so it's not a big deal. Well, I guess I will. Well, conclusion. Well, let me give just a 1 minute conclusion. Well, basically, I have the first step that I was dreaming of sometimes when it was actually the shock. I mean, if you want to do more asymptotic limits or whatever, the first things when you want to use this kind of thing is stability, because I mean, when you relative entropy in this case is really L2 stability. You need L2 stability. Well, at least we got it for shock. Well, up to this translation, otherwise it's wrong. But we got it in the way that we have a certain structure, we keep it. Okay, so it's very strong in these things. In order to go further, I think that actually, well, to go to trying to get asymptotic limits is actually, I think, still very challenging. And I think that the first thing, I mean, the thing is to remove this, is linked to remove this trace property. Because basically you don't want to say that you have to have a good sense of trace. So this is really the thing that we should have to remove. And it seems to be not easy. It seems to be actually kind of difficult, perhaps not possible. I mean, I think this is related. The fact, and at the end, what is the plan? What is the thing? Because actually we know there is some other result for asymptotic limits. Basically, I forget to talk about, of course, the work of Bressan and Yu, which is basically a completely different theory based on L1, very nice for small BV, so perturbation of BV. And in this context, they are able to go from Boltzmann to conservation laws. But in terms of philosophy, all their work mean that actually if you want to go from Boltzmann to, for instance, or whatever, kinetic model to a limit model, you need to have a fine structure of what happened, and especially at the kinetic level. Okay, you really need to find all the structure. And what I've learned actually from Claude Bardos is actually when you have something, a strong stability of the limit case, basically consistency is enough, because everything is driven by this strong thing. So the idea is, well, can we not? Okay, for shocks, because of course shocks is more tricky. So this is of course the main things, and at this point I don't know, and I'll stop here.
Thank you. Very impressive. Questions?
Okay, maybe I have a comment there.
Yeah.
Thanks for mentioning me, I don't know. But so I can feel I can make a comment that will be mathematical fiction. You know, there are old results on the stability of shocks which go back to Maida, and they result in any space dimension. That's in the small. He has a big paper on the stability of multidimensional.
Oh yeah.
Now I wonder, in all in this board that you wrote, what is really 1D?
Yeah, and actually, well, if you talk about the this kind of problem, the uniqueness is not known. The existence is known. The uniqueness is still open for those shocks, multi-D shocks.
No, but you assume that you have simple shock.
Yeah, and actually, this was one of the ideas. What would be? Can we go to this? Can we get uniqueness in the multi-D case when in some way we know that we have smooth solution on the left and on the right?
Yeah.
And well, here, let me do a picture.
In space.
Yeah. Let me do a picture is that in multi-D, what you want to move, because basically here.
I want to move the surface, the interface.
Exactly. Because now you are multi-D, and basically when you are 1D, if you see that 1D, this is one plane, and basically I say I just push my plane. Now if you follow the same thing, what you will, if you have something here, yep. Well, this is the normal derivative that I have of the velocity that I want. If I do exactly the same, if I compute my x prime, it will be with respect to the normal derivative.
Sure.
So the question is, can I keep something which has enough regularity for my surface to go on? And in general, it's not true, because my solution U is just no regularity. But if you say, well, but on the left is regular enough, you know, exactly in the Di-Perna setting there is a hope to push there. Yeah. This is one of the programs. So.
Any more questions?
What happens if you have a middle shock that you perturb? What do you think happens in this case?
Exactly. Well, actually, this is the idea to try to put it to hydrodynamics. Of course, in dynamics, you don't want to put one point. You want to see a layer. So this is so the idea is would be to actually the way I construct my x, not do it pointwise, but do it in a sort of boudin, to take a French culinary name. I mean something which has some and to say that actually I don't want to do this, but to have a sort of boudin like this and to construct it from. Basically, what I do is I integrate like this and cut it, with the Dirac, and do it smoothly. And for the other one, smooth like this, okay? And then in some way, it smooths out your X prime. In the layer, you can use consistency in order to do things. You construct it, and well, it doesn't work. It does not work because here, if you do the same thing, saying, well, let's deal only with the left, and the right will be fine. The right is not fine in general. And this is really linked to the fact that you can have oscillation in your layer. It's really linked to this. You have a layer, and the layer makes that actually what you get is not what you want. And well, to have oscillation in the layer is basically the same problem that getting a strong trace. That's why I say that actually to go further, of course, it will be exactly as you said, putting a sort of a thing like this, but the deep problem is of the same kind of problem that gets rid of the strong trace property.
Thank you again for the talk.